Alrighty, so off we go. Last time we were talking about change of variables. Remember, the big idea of change of variables is that it's kind of a rip-off. Okay, time to get started. So it's whenever y'all are ready. Okay, all right. So it's kind of a rip-off of substitutions. It's in fact, substitutions are the one-dimensional special case of change of variables. So the big idea is if you have your x and y variables that are written in such a way that they are functions of u and v, you can just plug that right in. Wherever you see x and y, just plug that right in. And what had been written in terms of x and y now is written in terms of u and v, and so you can think of this as an integral in the uv plane. The only catch, the only extra little detail, is you do have to recognize and account for the fact that that little piece of area is not the same as that little piece of area. Right? They're clearly different. This function g could be all kinds of wacky. It could distort the plane, it could stretch the plane, areas could come out bigger, they could come out smaller. So exactly how much that stretches things just has to be inserted in recognition of the fact that this area in your output, dA, is stretched accordingly from that input piece of area, du dv. Right, so that's really the only part of change of variables that isn't just plug it in, right? Is this stretching factor? Right, just make sure to remember to insert your stretching factor. Make sure to know the formula for the stretching factor. And let me get to that. Let me erase all this extra. Well, in fact, let me do it like this. That stretching factor is computed by that formula. And just as a reminder, the majority of the heavy lifting of that formula, of course, is done by this determinant, namely that determinant, which for notational reasons is very convenient to write like this. We write it as if it's a fraction. It's not a fraction. Clearly a determinant, right? Definitely not a fraction. But it kind of behaves like a fraction, and we saw one way in which it behaves like a fraction. Again, this stretching factor. Don't forget the absolute values. That stretching factor, keeping in mind that's what goes here, that's what we are multiplying by du dv. Well, you can almost kind of see that du dv cancels with, again, forgive me, that du dv. It's almost as if that's true. It's 100% not true. Right? That's not even a fraction. There's no cancellation. But writing the notation this way helps us make sense out of it. Right? Okay. All right. And then we did an example last time. This example, to be fair, was highly manufactured in the sense that the domain that we were stuck with, seemingly, at the start, was given as an image, right? But furthermore, we were given the function by which it is an image. That's manufactured, right? Most of the time that doesn't happen. Most of the time you have to come up with your own change of variables function, right? And that's what we're going to talk about in the remaining examples that we're going to see today. Okay. All righty. So let's see here. Here's a couple of change of variables functions that can be convenient sometimes. This, of course, is a translation. Right? I'm sure you all recognize this is translation by the vector a comma b. Whatever you put into this function, what comes out will be the same thing plus a comma b. Right? So that shifts things according to the vector a comma b. Here's the thing. Keep in mind, when you do change of variables, you are doing a pullback, right? And so if you have a function, if the action of your function, hypothetically, is to just shift everything by some vector a comma b, right? Well, pulling back turning this integral into that integral, we're going the other way. And so your image, the domain that comes to you, that to which you want to apply a change of variables, that domain that comes to you, when you turn it into what its pre-image is on the left, you will effectively be shifting it backwards by a comma b. In other words, shifting it by minus a comma b. Right, so you always got to keep in mind that you're undoing because you're doing a pullback, right? And so a function that shifts by a comma b, what does it do to my domain when I do change a variable? Well, it translates backwards. Okay, so likewise for various other examples, you could imagine a stretch in the u direction or in the horizontal direction, whatever you want to call it. Okay, yeah, sure. That change of variables stretches, which means what it does to your domain when you do a pullback is it squishes. It undoes what the transformation does. And likewise for a rotation. So I'm going to give you an example of this rotation because I think it's the most confusing of these three examples that I'm giving you here. Y'all can think of your own examples of this kind of thing. Good exercise. I hope y'all will give that a try. So here we go. Got an integral that comes to us here. This integral right here. My domain for this integral is this square, which y'all can plot those points, of course, and it's that right there. So there's our domain. How are we going to do this as a double integral? How are we going to set this up? How are we going to make an iterated integral out of this? And, well, you can slice it up, right? Section 5.2, just slice away. The problem is you're going to hit corners, right? And so depending on which way you slice, for example, if you slice this way, well, then you're going to hit that corner and that corner. And you're going to have three integrals. And analogously, if you slice the other way. Okay. So the way we avoid this is to say, hey, you know what? That domain for the integral I'm interested in, I would like to rotate it. I would like to do this. Wouldn't that be nice if I could rotate it clockwise to turn it into a much more convenient square? Wouldn't that be nice? Okay, well, keep in mind, sure, we can do that, but that's going to be the undoing process. That's going to be the pullback. In the pullback, I would like to have a clockwise rotation of my given square. Okay, now how am I going to make a pullback a clockwise rotation? And the way we do that, of course, is to have the original function be a counterclockwise rotation. If our original function is a counterclockwise rotation, so in other words, this rotated by t counterclockwise, from what it had been, which I like to kind of shade there because it's not there anymore, right? But it had been here, a counterclockwise rotation. Then, sure enough, my blue square is the image by t. This is the image by a counterclockwise rotation of a much easier domain. And so when I do the pullback, then as I wished, in doing the pullback, my blue undesirable domain turns into my green awesome domain. Does everybody see how the backwardsness works? Okay. All right. Okay, now details. Yeah, there's a bunch of details here. Y'all do have to remember how to do rotations, right? So again, our linear transformation here, what is our change of variables function, is the counterclockwise rotation, and I hope y'all will recall the way to do a counterclockwise rotation is by way of this matrix with sines and cosines written like that. Again, excellent exercise. the big ideas here, this is all linear algebra, right? But the big ideas are that linear transformations are represented by matrices. Matrices are understood by their columns. Those columns are the images of the standard basis vectors. So all you got to do is take your standard basis vectors, rotate them by whatever angle theta, and then just look at those images. Those make your columns. So great exercise. Now again, as always, I just want to remind you, if you have any questions, if you get stuck, if you're not sure how to get started, if you didn't understand what I just said in the first place, come to office hours. I'll be very happy to straighten that out for you. It's no problem, right? And a lot of students need a little help on this, and that's totally fine. Come talk to me. Okay. Now a little bit of geometry, and this this kind of detail anyway is something y'all can think through on your own. Given the coordinates at that point, we can conclude that this angle here is pi over 6, and taking that angle and plugging it in for theta turns our matrix into that. And so here's our change of variables. Well, see, let me put all this together. Get rid of all of okay. So our change of variables function is this right here. Everybody on board with that? Okay, so now it's just a matter of using the formula. And again, you know, we have our formula right back here. Yeah. So basically just plug in. Don't forget to insert your stretching factor. So here we go. We're going to compute that stretching factor. Keep in mind that if we want to take partials of x, I actually have an explicit formula for x. And you can see this two different ways. One is you can just remember, look, x is the first output coordinate from t, right? I've got a formula for t. It says right here that x is the first output coordinate. And so x is that right there. And how is that computed? Well, it's this dot product right there, because that's how matrices multiply by vectors. Everybody on with that? Everybody happy? Okay. Right, and then you take the various partials, et cetera, et cetera. Then you compute the determinant, and the determinant ends up being 1, which at first glance you think, what a shocking coincidence that we did all of this calculation. We did trig and linear algebra and partial derivatives, and you're telling me the answer turned out to be 1? What are the odds? Right, from a computational point of view, maybe a little surprising. Then if you think about things a little bit more sort of geometrically, in fact what we were doing is keeping track of how much areas are stretched when you rotate. And I think it's a pretty easy geometric appeal. When you rotate, there's no stretching at all. Right? It's just nothing's getting bigger. It's just kind of changing its orientation. Does that make sense to everybody? So this is actually a very believable result. In fact, if I didn't get this result, I would have an easy argument showing that I had made a mistake. It kind of has to be 1. All right. Okay. That said, do keep in mind, on an exam, the intention of an exam question is always important to advise how you give your answers, because of course you want to give us what we want to see, right? And on a question like this, we're looking for your proficiency with the calculation, right? So give me the calculation, but nevertheless, in the real world, right, outside of this course, yeah, geometric argument, totally fine. All right, so let's see what this does to our original integral. Well, my original integral was, the integrand was this. How am I going to write all that in terms of u's and v's? Well, don't forget, x is that dot product, which means that x right there is just that. Right, so the easy thing to forget. Lots of students, you'd be surprised. Lots of students, they kind of get stuck. They maybe compute their stretching factor, but they don't know what to do with the integrand. Just try to remember, the change of variables function itself tells you how to convert the original integrand. Right? It is the formula for x and y, or whatever your output variables are. Okay, so likewise for y. Don't forget to include your stretching factor, and of course the stretching factor is the absolute value of this. Wrong color. I already used that color. The stretching factor here is the absolute value of that determinant that I just computed. So absolute value of 1. Okay. And there's your new integral. Now, again, let's take a look. This was our original integral. Here's our new integral. Which one looks better to you? And I'll bet you, at a first glance, you're probably thinking, you know what? I'll take the original green integral. Thank you very much. All this business over here has got weirder numbers in it, and it just doesn't look as desirable. Don't make that mistake. Don't fall for the illusion, the allure of a simple integrand, right? That's single variable calculus talking, right? In single variable calculus, the integrand is the thing. The integrand is what makes an integral hard or easy. And the domain is just numbers you plug in at the end. The domain is rarely of interest, right? Not so with these questions, right? This green integral, we agreed that if I'm going to compute this, I'm going to have to slice this up into 3 separate domains that have non-flat edges, which means that there's going to be functions in the bounds. It's not that it's not, you could totally do this. It is, however, 3, kind of medium difficulty integrals. This is one integral. The domain here is my new square, my pullback square. The domain here is this right there, which is awesome. Whereas this integral here, now it looks good at a glance, but there's its domain, and that's not good. Nobody wants to deal with all of that nonsense. So yeah, there's a couple of weird constants in here, but they're just constants, not that bad. This blue option, way better. Yes?
Let's say just for fun that we didn't see this on a test.
Yep.
And we just decide, hey, I'm going to integrate
I hear you.
that weird square.
Right.
And if we end up working through it, get the right answer, show a correct thought process throughout the entire thing, or still get marked out just because we didn't see it.
Marked down is the wrong term because it suggests I'm taking away something that you already had, right? What I would say is if you do the problem the hard way when there is an easy way, I mean, it does show that you didn't see the easy way, right? So you got to keep in mind, so high schools very often have the wrong philosophy on this, and they focus on the answer. It's only about the answer. Math is about answers. We just want the answer. If you get the answer, then okay. No, it isn't. Math is not about answers, right? I'm sorry, soapbox speech, right? This is one of my little pet peeve topics, right? It's not. Math is about ideas and understanding and reasoning, right? And so if your work shows that you misunderstand an important idea or don't have proficiency with an important idea, then of course your grades can not be as good. I mean, does that make sense? I mean, it's going to be, so the point is the focus of the grading, right? And the focus of the grading is what I can infer from what you've written that you understand about the ideas relevant to that question. Right? So I hope that makes sense. Yeah. Okay. Cool. All right. So a couple of little formalities that I just kind of have to, this has to get said. This is not going to be an issue in most cases, but technically we do need our change of variables function to be continuously differentiable. We're not going to be in any situation where we would want otherwise. So this is just a formality. One thing that is a little sticky, the change of variables function has to be invertible. And this very often gets left out of theorems about this. And I can show you counterexamples where it just straight up doesn't work if your change of variables function is not invertible. So you do have to some extent, you've got to look at your domain and see what's happening. And I think it's pretty geometrically clear in this case that this process of, I'll do it over here, this process of rotating is truly invertible in the sense that I can undo it by just reversing the clock, and every point in this green square rotates to a point in this blue square. And there's a 1-to-1 and on-to, right? There's a bijection. There's no sort of like folding over, overlap, duplications or anything like that. Okay, so just something to keep your eye on. Okay, here's a cool fact. We talked previously about this notation, writing the stretching factor. Okay, don't forget the absolute values, but writing, the bulk of the stretching factor as a fraction, because I claim it behaves like a fraction, and we've already seen one version of how it behaves like a fraction. So I'm going to show you a different way that it behaves like a fraction. Now, let me remind you, we write our stretching factor like this, with the understanding that we're taking the partials of the outputs. Keep in mind our function goes to the right here, so x and y are the outputs, and we're taking the partial of our outputs with respect to our inputs. Okay. Now, if this were, as it must be anyway, a invertible change of variables function, then I could talk about its inverse. I could ask the question, what would be the stretching factor for this inverse? Well, this inverse, let's see here, I've already forgotten the colors I used. U and V are the outputs for that inverse function. So if I want to know the stretching factor, I take the partial of the outputs, now U and V, with respect to the inputs, again, to my inverted change of variables function. My inputs, now x and y. Right? And so again, you'll notice I'm using this shorthand notation. Okay, now the cool observation to make is that, now I hope this part is pretty clear, and that is that if you look at a function which is the composition of those, nothing happens. Right? If I take some little region of the UV plane and convert to x's and y's and then say whoopsie and then go right back and have the exact same set in the UV plane, there's no stretching. It's literally the same. And so that stretching factor kind of has to be 1. And so that means that the product of that stretching factor and this stretching factor, that product has to be 1. Or said differently, those fractions that look like reciprocals of each other are reciprocals of each other. So it's a lovely little convenience, and yet another reason why I like this notation. This stretching factor, we write it as a fraction, not because it is a fraction, it's not, but because it behaves like a fraction. Everybody on board with that? All right, so let me show you how convenient this is. There are some situations that come up very naturally where it's just easier to think of the change of variables function going the other way, by which I mean we're going to want to take some undesirable domain over here and pull back, we're going to want to say pull back to get some nicer domain over here, except it's not pulling back because, and again this comes up naturally, sometimes our change of variables functions go in the opposite direction, seemingly the wrong way, and I want to show you how to deal with this. Okay. All right, so here we go. Here is a version of the classic first example of situations like this. This is a very tricky idea, by the way. I did not think of this. I don't think you should expect that you should have been able to think of this. This is an example that all of us get to benefit from somebody else telling it to them and pointing out, and this is very, very clever. Very clever. Okay. So, here's a weird domain. It's bounded by these 4 curves. There's a pair of curves that are level sets of x, y, and then there's another pair of curves that are level sets of xy squared. And both of those are vaguely kind of, as I have drawn here, x and y are sort of working against each other. When x gets bigger, y gets smaller, right? They both have the same approximate look, but they are a little different because of the exponent there. And you can see that there is a little region that's bounded in between here. All right, and so let's suppose you want to do an integral on that domain. Is that cool? Everybody happy? Now, I know this looks manufactured. It really does. As it turns out, and I think this is just for your curiosity, this shape actually arises really naturally. If you take a class in thermodynamics, which I imagine engineers probably have to do, take a thermo class and study this thing called the Carnot cycle, or the Carnot engine. It is sort of a theoretical engine, sort of an abstraction. That is very important in understanding the fundamentals of how thermodynamics, sort of the limits of engine efficiency in some sense. And so this is a picture that very naturally arises in that discussion. So this is not totally made up out of whole cloth. This comes from a very natural example, and y'all will see that eventually. Okay, so how do I deal with this domain? It's obviously terrible, obviously undesirable. It's going to have corners. If I sliced it in any of the usual ways, it's going to be 3 separate integrals. Nobody wants that. So here's the clever move. Gosh, I wish I thought of this myself. I didn't, but here it is. Here it is. Whatever your equations are, let me pull back on that just a little bit. If your equations are 2 level sets of one function and 2 level sets of another function, then something awesome is going to happen. Now, let's just take a quick moment to recognize that is what we have. In this case, we have 2 level sets of xy and 2 level sets of xy squared. Okay. If that happens, take those 2 functions and make those your change of variables functions. Let's see here. Do it like this. That is your change of variables functions. U and V, just set them equal to whatever these 2 functions are, whose level sets give you the bounds for your domain. Does everybody see the setup? Okay. It's critical that these be level sets. So let's not be too subtle about that. These have to be level sets. It's not good enough for them to just take whatever equation. Don't just take the left side of whatever equations you were given. You've got to play with them as needed, if necessary, so that they are written as level sets. We need the functions for which these are level sets. Okay, so now just notice when we write this down, according to this trick that I'm claiming, notice the function goes this way. X and Y are inputs. U and V are outputs. And as we discussed, this function's going the wrong way compared to what we're accustomed to. All right. Now, for whatever it's worth, it is possible, totally doable in this case, to just solve for x and y and turn that function right around and make it point the right direction. You could totally do that. 2 things. It'll actually be harder that way. Secondly, this is serving as an example of a technique. We're interested in the technique, not the answer, right? So this serves no purpose to switch it around. And then finally, sometimes you cannot solve for x and y, right? I've made this one, I didn't want to get lost in algebra, so I've made a nice, easy example. And yes, this is, you can reverse this. But there will be examples where you either can't do it or it would be impractical to do it. So let's pretend for the purposes of this example that we cannot solve for x and y on their own. Is that cool? All right. Okay, so I'm going to take the only partial I know how to take partials of, namely I'm going to take partials of u and v with respect to x and y, because that's what I have formulas for. And plug and chug, y'all can do that calculation, and that ends up being xy squared. Now, that's for this function going that way. So if I'm interested in going the other way, and keep in mind, when I say going the other way, I mean if I'm interested in pulling back through a function going the other way, and that is indeed what I want to do. I want to go to the left, which means I need to go backwards through this purple function. You just take the reciprocal. Again, these behave like fractions. It's very convenient. So notice all I've done is take the reciprocal of what I computed. Is everybody happy? All right, now let me confess, it is very easy to get confused and turn around backwards. And I wait a second, I want to go backwards through, but I want to do the backwards of the, oh my gosh, and you can get turned around and where you just can't get it the right way. How do you keep it straight? This is where this notation, I think, really shines. And that is, look, there's no getting around the fact that we were given an integral in the xy plane. That's this ugly domain that I have to deal with here, right, that I don't like. It is in the xy plane. It is an xy integral. You see the differential right there, dx dy. This is what I need to compute. And, well, if I want to compute that, I got to figure out how to rewrite dx dy. How am I going to rewrite dx dy? How am I going to write dx dy as something times du dv? What do I multiply by du dv to get dx dy? That. And just think about the fake cancellation. Again, it doesn't actually cancel, right? But pretending that it does, taking advantage of the fact that it looks like it does, is a fantastic way to help you decide, wait a minute, which one of these stretching? Do I want partial xy, partial uv? Do I want partial uv, partial xy? Which way does it go? Let this be your guide. Is that satisfying? Okay. All right, and conveniently, that's what I just computed. I hope I got the colors right. That's therefore Okay, so yay, we're almost done with this example, except here's the ugly side of things. This resulting integral, I've got a new domain, I've got my du dv, the stretching factors in there. It's all looking good, except my integrand is not written in terms of u and v. This is where I would like to plug in. This is where I would like to be able to say, well, x is the following expression of u and v, and y is some other expression of u and v. I'd love to plug that right in there, but I don't have it. Right? Again, by assumption, I do not know how to solve for x and y. Okay, so what you do in this situation is, I'm sorry to say, not going to be just a regular old technique that you can just always turn the crank on. You do have to think a little bit creative here. I'm going to point out, though, that you don't need to know what x is. You don't need to know what y is. All you really need is to know how to rewrite this integrand. And so what we're going to do is take the integrand itself, not x, not y, the integrand itself. Stretching factor included, everything together. And now we got to play a game where we speculate how I might possibly write this in terms of u and v. And I'm going to reason as follows. Now, this is peculiar to this example. This is not a general method. But in this particular example, I think, look, what I have is a product of powers of x and y. Okay? I need to write it in terms of u, which is a product of powers of x and y, and v, which is a product of powers of x and y. And now here becomes here's the question that I have to answer creatively. I mean, like, what would I expect algebraically to have to do to products of powers of x and y to produce a different product of powers of x and y? And so thus begins the algebraic speculation. And my best guess here, I think this is reasonable, and by the way, this is also right, is that you should take a product of powers of those products of powers, because we know that will produce a product of powers just like we want. And then it's just a question of playing the game and trying to figure out A and B. Does that make sense to everybody? Did everybody see the sort of the connect the dots, the little thought process that I went through there? Okay, so it's going to be different for every example. Don't make the mistake of thinking that you can always, where's my little button? There we go. That you can always just, okay, it's always a product of powers. No, it depends on what kind of structure your integrand looks like. And it depends on what your U and your V look like. And every example is different. And you got to tailor your speculation to that difference. Okay. All right. And everything else here is algebra. Y'all can play this game. A little bit of linear algebra comes up. Make sure you remember how to do all that stuff. And it turns out this is that now in terms of U and V. Okay. Okie dokie. Alrighty. Real quick, let's talk about where this formula comes from. The stretching factor, remember I swept this under the rug when we first got started. As I said at the time, there's enough going on. We've got to keep track of how do you implement this, and we've got an old domain and a new domain, and things are going backwards, and how do you choose your change of variables function? There's a lot going on, right? So now I do want y'all to see where this formula comes from. And remember, the big idea is we have some little input area that goes into our function, and then out comes an output area, which is going to be a little parallelogram, well, approximately, not exactly. And I need to know by what factor is blue bigger than green. Well, to make sense out of that, the first thing I'm going to do is try to understand these edge vectors. And it turns out there's a lovely, very convenient way to think about that edge vector. And that is, it's the image of this edge vector. And image by what? What is it that we do to input changes to get output changes? Well, we multiply by the derivative matrix. The derivative matrix is the thing that turns input changes into output changes, and that's what these edges are, right? This green vector represents, could be thought of as representing, a process by which I start at this edge and move to that edge. So this literally represents a change in the input. Likewise, the blue is a change in the output. Is that cool? All right, so that's the first observation. Second observation is that we can just compute this area. It's in fact just a parallelogram. Well, it's approximated by a parallelogram. Not going to be exactly a parallelogram. But I have a formula for how to compute the area of a parallelogram in 2 dimensions. It's this chapter 2 formula right here. I take my 2 edge vectors and I make those my columns. And take the determinant and take the absolute value. Is that cool? Everybody's happy? And everything, it's all downhill from here. It's just a matter of sort of thinking through the algebra of, how do I deal with this great big determinant? Well, I have a scalar factor there, and scalars factor out. And then there's another scalar factor right there. Scalars factor out, and now I've got this matrix, this matrix to deal with. How am I going to deal with this matrix? And there's various different ways to see that is just DG. I would encourage you to think of this as DG times a matrix whose first column is E1 and whose second column is E2. That's just a little bit of matrix multiplication, linear algebra. Right? And now what is this matrix whose first column is E1 and second column is E2? It's the identity matrix. Right? And this being the identity means that this is literally DG. Hope that's satisfying. Linear algebra just won't go away. It just keeps being useful all the time. So something to make sure you're comfortable with. Okay. All right. So we that's where the formula. Sorry. I almost spiked the football on the 2-yard line. Let me wrap it up here. The point to all of this, again, was we're trying to figure out how to take input area and turn it into output area, and what is the factor by which that gets stretched out into that. Well, I just computed that blue area, and it is the green area times the stretching factor that I was looking for. So that's how I know that expression is the stretching factor. Everybody happy? Okay, 3 dimensions. Good news. Almost exactly identical. Practically identical. Again, we might have some ugly domain, and wow, what a nightmare this monstrosity would be. I don't even want to think about how many different, if I slice this up according to our triple integral methods, right, I'm going to hit corners, and I'm going to be side-swiping faces, and I'm going to have the cross-sections themselves are going to be bumpy and wiggly and weird and all sorts of just endless nightmare of problem. Right? If you can find a way to view that as being an image of something simpler, like a box, that's the dream domain, of course, for a triple integral. Right? If you can find some way to view it as an image, then you can do the usual pullback, a lot of which is just plugging in x, y, z, again, are literally g of u, v, w. That's just plugging in your change of variables function. Whatever function turns green into blue, just plug it right in there. And then don't forget your stretching factor. And your stretching factor is highly analogous to what it was in the 2-dimensional case. This is another nice exercise, something to think through. You can totally do this. You can totally show that stretching factor as this determinant. The way you're going to do it is going to be morally equivalent to this. It's just 3-dimensional instead of 2. But structurally, it's going to be just like this calculation here. So that's a good thing to chew on and, again, think about. And I would encourage you to try to write it all down and just get all those details on paper. And as always, come ask me questions if you get stuck on anything there. Okay. So, so same formula, in effect, for the stretching factor. And let's see this in action. This is another one of these really clever. I don't want to get too far ahead of myself. This is before we get to the example, nice little theorem. This is an easy theorem to prove. This is a 30-second proof. So make sure you can prove the following. But when you are looking at a linear transformation, that linear transformation represented by a matrix, the derivative matrix is the same matrix. All you got to do here is just make up, like a generic matrix A, like have the coordinates be A, B, C, D, E, F, G, H, I, something like that. And then just literally compute the derivative matrix by the usual chapter 2 formulas. And then you'll just notice, oh my God, that's exactly the matrix I started with. So good exercise to check. Okay, really neat example. And again, one of these examples where I never would have thought of this myself, right? We all get to benefit from clever ideas that our predecessors have come up with. So here's the benefit. If you have a domain that is a parallelepiped, something like that, This is a nightmare. Nightmare. And it's tempting to look at this and think, oh, well, it's just got flat faces. I mean, how bad could it be? This is a nightmare. And let me just point out to you how bad this example is. If you were to come at this section 5.4 style, just in other words, a triple integral, I'm just going to start slicing. Parallelepiped has 8 vertices. One's the start, one's the end. That leaves 6 corners in the middle that you're going to slice through. 6 of them. That means you're going to do 7, at least, separate triple iterated integrals. And by the way, it's actually much worse than that, because those cross sections are not squares. Those cross sections are triangles and parallelograms, and actually some of them are hexagons. That's a little geometric challenge, something to think through. In some cases, some of those cross sections are hexagons. Each one of those, as you slice it up, is going to be a bunch of pieces. If you do this brute force, 5.4 style, you're going to have like 30 separate integrals. It's a nightmare. Does that make sense to everybody? All right. So how do I get around that? Here's the answer. Again, this is a beautiful trick. I wish I thought of it, but I didn't. Somebody showed me this. This is brilliant. Here's the trick. Whatever the vectors are that are the edge vectors for your parallelepiped, as you'll notice given in this example, whatever those edge vectors are, those are your columns for the matrix that defines your linear transformation, that is your change of variables function. That's the move. You just got to remember the move, right? For a parallelepiped, pull that trick right there. And I claim awesomeness ensues, and this is just a matter of kind of thinking through. I claim that the pullback domain becomes the unit cube, which again, that's the dream. For a triple integral, it doesn't get any better than the unit cube, right? World's most convenient domain. How to see that? Well, zoom so I can see a little better. Let's just think about where does this edge go? What happens when I take E1 and plug that into this linear transformation? Well, plug in E1, I've got matrix times a standard basis vector. That will give me as the output that first column, which by construction was my first edge vector. And likewise for the second, and likewise for the third. And then by linearity, the cube maps onto the parallelepiped. Real clever, super clever. Wish I thought. Everybody happy? Okay, so yeah, you remember that little trick, and then it's all downhill from there. Let's see if I can get this all onto the, okay, I think, yeah, that'd be good. So I am going to have to compute the stretching factor. I am going to need the derivative transformation for that change of variables function. We have a theorem that tells me that in such cases, the derivative transformation is, well, whatever that matrix was in the first place, which, is this. We've already written down what that matrix is that represents the transformation. So, bam, there's our derivative matrix. And therefore, that's the thing whose determinant is my stretching factor. So you just got to punch up the determinant of that matrix. Right? It's the determinant of that matrix A. There's your stretching factor. Everybody happy? Alrighty. Okay, and let's see, how are we doing on time? I'll bet you we have 17 seconds. Okay, so there's no way we're going to get anything done there. I am sure I owe you time. We'll draw the line right there. Have a good rest of your Monday. See you later.
you have office hours?